Hello students, myself Dr. Pranna Magdo, and now the exams are nearing. My MSc second year students have suggested me to confine the whole series of the nuclear and particle physics in just 4 lectures. So they want me to confine one unit into the one video. Okay, so let us start with the first unit, which is a nucleon interaction. This will help you to understand the concepts within just one video. Okay, so in the first unit we have dealt with the introduction to the nuclear and particle physics, and for the first time we have seen the formula for the nuclear radius. Okay, we have seen what is meant by actually nucleus is a quantum mechanical entity, and you cannot say the radius of the nucleus, you can say the radial extent of the nucleus. Okay, and nucleus is not like a hard ball, it is not having a sharp boundary, it is not a classical mechanical entity that we have seen in details in my previous videos. Okay, so the radial extent of this nucleus can be evaluated by using the formula R is equal to R naught a raised to 1 by 3, where R naught is a shell cap and A is the mass number of any element. So by using this formula, starting from the lighter nuclei to the heavy nuclei, you can evaluate the radial extent of all the nuclei. Now let me tell you that this radial extent extends from 2 femtometer to the 8 femtometer, starting from the lighter nuclei to the heavier nuclei. So the range of this nuclear extent, radial extent, is from 2 to 8 femtometers. Okay, then we have seen this is how generally the nucleus looks like. Then the up to the certain distance, the charge distribution is constant, and then afterwards it goes on decreasing gradually. Okay, so this is how the nucleus looks like. So we have seen the graph of the charge density versus the distance. Okay, so in which we can see that like this. So this is the charge density. So the charge density remains constant up to certain time, and then afterwards it goes on decreasing. Okay, so this is how the this nucleus looks like. So this charge density is constant up to some distance, and afterwards this charge density goes on decreasing, and this distance, so this is called as a shell cap, which remains constant, and its value is taken to be as 1.2 femtometer. Okay, so this is how we can evaluate the value of radial extent for any nucleus. Okay, then we have seen the Deuteron system. See, in the atomic and molecular physics, you study the states of the hydrogen atom. Okay, similarly, when you deal with the nuclear and particle physics, the smallest nucleus you can study, that is a deuteron, because the deuteron, it is having one proton and one neutron. Okay, so if you study the case of this one neutron and one proton interaction, so you can apply the same potential, whatever interaction between them, to the heavier nuclei. Okay, so the basic element to understand the nature of the nuclear interaction, it is a deuteron. Okay, so what we know about the deuteron is its binding energy is 2.225 MeV, whereas its total energy, of course, it is minus 2.225 MeV, and binding energy per nucleon, it is 1.112 mega electron volts. Okay, now this diagram is very much important, which is called as a square well potential. Okay, now this is square, what is mean by this square well potential? Now suppose if you have a proton and if you have a neutron, and which are very at a far distance from each other, and when they are nearing to each other, when they come closer, okay, up to some distance, so as that they start interacting with each other, now that distance is called as this R naught. Okay, so after this R naught, these two means whatever it is, a proton neutron or two protons, or a proton neutron or a neutron neutron, whatever pair it is, So it is called as a nucleon interaction, NN interaction. So whatever nucleon is there and another nucleon is there, so both of these nucleon will have their own field. Okay, so the R naught is a distance, so at that distance they will start to interact with each other. Now for the distance R less than R naught, there will be some interaction potential between this proton and neutron. Okay, and for the distance greater than R naught, there will not be interaction between this proton and neutron. So this is what this nature of the interaction between the two nucleons has been shown by this square well potential. Okay, now see here, I have written the conditions. We have divided it into two parts. So R naught is the boundary. So if the distance is less than R naught, there is an interaction. If the distance is greater than R naught, there is no interaction. Okay. Now R is less than R naught. For this distance, there will be some potential which we have taken as a minus V naught. And for the distance R greater than R naught, there will not be any interaction. So the interaction potential will be 0. Now, once we have understood the two regions for the nucleon-nucleon interaction, we have applied the Schrodinger's time independent equation for this two potentials, and then we have calculated the two equations for the. Now by applying Schrodinger's time independent equations for these two regions, we have evaluated the wave functions for the region 1, that u1 is equal to a sin kr, where k is equal to square root of 2 mv naught plus e upon h cross square, and similarly the wave function for the second region we have evaluated as d is equal to e raised to minus gamma r, where gamma is square root of minus 2 me upon h cross square. We have also evaluated the boundary conditions where u1 is equal to u2 at r is equal to r naught, and by using all these three equations we can conclude, we have drawn the two conclusions that V naught, see here, by using these three equations we have calculated V naught is equal to minus 36 mega electron volt. Okay, now see here, this V naught is equal to minus 36 mega electron volt. So this is minus 36 mega electron volt, and the total energy is minus 2.225 mega electron volt. So if this is a 36, so minus 2.225 mega electron volt will lie somewhere over here. We can say that thus the deuteron is a weakly bound system. See here, the depth of the square well potential is a minus 36 mega electron volt, whereas the total energy of the deuteron is a minus 2.225 mega electron volt. Okay, so we can say that this deuteron is a weakly bound system. Also, we have found the wave functions of this deuteron potential of these two particles, proton and neutron, as A is equal to U1 is equal to A sin kr. It means that in a region 1, it will show a sine function like this, okay, and in a region 2, it is exponentially decaying function like this. Okay, so here we can also see that for the most of the time this wave function is outside the potential well. Therefore, we can conclude that this deuteron has no excited state. It means that it is a weakly bound system. For most of the time this wave function is outside the square well potential. It means that even if you are supplying a small amount of energy to the deuteron, it will not go to the excited state, but rather the proton and neutron will separate out. Then we have seen the NP scattering. Now suppose if you have taken a proton or a neutron as a target particle and another neutron and proton are coming from with high kinetic energy. Okay, so they will interact with the rest proton or the neutron, and they will get scattered from that. So this is called as a scattering experiment. Now in this scattering experiment, we have calculated one term experimentally which we call it as a scattering, differential scattering cross section, which is called as a sigma. Okay, let me write it here. So this is a differential scattering cross section, and this differential scattering cross section, it depends on many things, like obvious dependencies are there, like it depends on the number of target particles which are present, number means what is the intensity of the incident beam, and aerial, what is will be the aerial density, what will be the depth of that target. Okay, so these are the obvious dependencies, but along with this scattering cross section depends on, or it is a measure of the interaction between the neutron and the proton. Okay, so we have evaluated the value of this sigma, which is equal to dn upon d ohm Na into Np, where Na is the aerial density and Np is the number of the target particles. Okay, now this scattering cross section sigma represents the or it is a measure of the interaction between the neutron and the proton experimentally. Okay, now see here, we have also done the theoretical calculations for this interaction, and we have named that interaction as a phase shift delta. Okay, we have taken some wave function psi, okay, for the incoming particle, then we have taken the wave function at the detector. Okay, so we have by different quantum mechanical calculations, which we have seen in my previous videos. Okay, we have concluded that this phase shift delta is also the measure of the interaction between the proton and neutron. Now we can see that this is a phase shift delta is a theoretically dependent value on the NP interaction, where this sigma is a experimentally dependent value on the NP interaction. So there must be some relation between this sigma and the phase shift delta. We have evaluated this relation between the scattering cross section sigma and the phase shift delta also. Okay, now theoretically calculated value for the this scattering cross section was 5 bar. 1 bar is equal to 10 raised to minus 24 centimeter square. Okay, and the experimental value for this scattering cross section was about 20 bar. Okay, now what we have missed over here, why the calculations are not matching. Okay, so we have considered, so all these theoretically calculations by taking the potential to be central. Okay, it means that the potential depends only on the distance and it is independent of theta and phi. That is what we have assumed in our theoretical calculations, and there is a lot of difference between these two. And now when we have performed the calculations by taking the potential to be non-central or the dependent on theta and phi, okay, then we have found that these two values are matching, which says that these nuclear interactions are highly spin dependent. Though yes, this is the conclusion which we have drawn from this expression. I have written over here, nuclear interactions are highly spin dependent. Okay, so when the neutron and proton are there, and they, if suppose proton is coming very close to the, if the kinetic energy of this proton is increasing, okay, so it is able to reach the neutron. Okay, now we know that these are also made up of the fractional charges. If this is a neutron, neutron is made up of down, down and up core, and this is made up of, this proton is made up of up, up and down core. Now when this is nearing, okay, so that it can see the fractional charges on the neutron, okay, the spin interactions also play a role in the nuclear interaction, okay, or the what type of interaction is going to happen between this proton and neutron, that is dependent on the spin interaction between these two. Okay, but for that you need to have a very high kinetic energy so that it can reach the distance say less than zero point 0.5 femtometer, or say less than 1.2 femtometers. Okay, that we will see further. Okay, then afterwards we have seen so high energy NP interaction. Now we are seeing that whenever there is a interaction between the neutron and the proton, okay, that interaction is a spin dependent, that is okay. But now as you go on increasing the kinetic energy of the incoming particle, what happens here? So here we can see that this is a graph of a phase shift delta with respect to the kinetic energy of the incident particle. So this is a kinetic energy of the incident particle. Now see here, when the kinetic energy of the incident particle is less than less than 100 mega electron volt, so this L is equal to 1, that is not contributing so much. Okay, only S is equal to 0 and S is equal to 1. These wave functions are responsible for the interaction, or whatever nuclear interaction is there, that is due to the, so this S is equal to 1 and S is equal to 0. What is meaning of this? It means that below 100 mega electron volt, this neutron and proton, or the incoming proton, is not able to reach the neutron so as to see the fractional charges on it. Okay, the spin doesn't come into the play. Okay, so for that means the potential, whatever it is there for a neutron or what is experienced by this proton, that is a non-central potential. Okay, so non-central potential means it depends only on the distance and not on the direction. Okay, so this theta and phi terms are not coming into the picture. Okay, so for that term, so this L is not contributing, but as the kinetic energy goes on increasing, the incoming particle will start approaching more close to the neutron or the target particle. So at that time, so this L will start playing. So in this region, so the nuclear interaction will be very much spin dependent. And now if you again go on increasing the kinetic energy of the incident particle, what will happen? So it will try to reach a less than 0.5 femtometer, and there the repulsion will start. Okay, so you cannot force a proton and neutron beyond a certain distance. Okay, so the force of repulsion between these two start, and that is the point where the phase shift delta changes its sign. So above this 300 MeV, phase shift delta is positive, and above this below this 300 MeV kinetic energy of the incident particle, so this phase shift delta is positive, and above 300 mega electron volt, this this phase shift delta is negative. Now this phase shift delta has been, or the sign of the phase shift delta has been explained by using the quantum mechanical calculations and by taking this attractive potential and the repulsive potential. Okay, so this is the phase shift analysis by using the square well potential. Okay, attractive square well potential and the repulsive square well potential. Okay, so here we can see that the total energy is more. Okay, and afterwards it is decreasing. It means that the particle is being attracted, and in this case we can see that the energy is less and afterwards the total energy is increasing. It means that particle is nearing with a smaller energy and going with a higher velocity. It means that it is getting repelled. Okay, so by using these square well potential, we have given the explanation of the positive phase shift delta and the negative phase shift delta. There are few calculations over there, and then finally we have seen the particles involved in a NP interaction. Now we have seen the classification of the elementary particles, like particles are there, elementary particles. So they can be classified as leptons and hardons. And hardons can be again classified into mesons and baryons. Okay, so example is electron, neon, tau. Meson is pion, kaon and eta. And the baryons are proton, neutron, omega, lambda, sigma, etc. Okay, now see here. So suppose now this proton is a target particle which is situated over here, and the neutron is coming. Okay, so this is a incoming particle which is having some kinetic energy. Now if suppose the kinetic energy of the neutron is less, okay, so that it can reach only into this long region. Okay, as you go on increasing the kinetic energy of this neutron, so this will be able to reach this medium range, and if you again increase the kinetic energy of this neutron, it will try to enter into this short range region. Okay, so this we have divided into the three regions as a long range, medium range and a short range. So if the kinetic energy of the neutron is small, it can only reach into the long range. So for the long range interactions, pions are responsible. Now see here, according to the quantum electrodynamic theory, whenever there is an interaction between any two particles, that must be mediated by some exchange particle. Now, if the proton is here and neutron is here, due to the small kinetic energy, it is able to reach only in this long region. So here, if there is an interaction between this proton and neutron in a long range, so the mediated particle or the exchange boson will be pions, okay, with a rest mass energy of 140 megaelectron. Now as we increase the kinetic energy of this neutron, it can reach into this medium range, and according to the quantum electrodynamic theory, if there is an interaction between these two, the interaction must be due to some exchange of some particle, and that exchange particles are the two pions. Okay, now see here the mass is 140 megaelectron volt, and by using the Einstein's mass energy relation, we can say that as the kinetic energy of the incoming particle increases, okay, the mass of the exchange boson also must increase. Therefore here only one pion is involved, and here two pions are involved. Okay, so the mass of the exchange boson has been increased. Now if you again increase the kinetic energy of this neutron, so what will happen? It will try to reach into the short range, okay, and here the particle again, or the exchange particle, will be more heavier than a pion. Okay, so omega is a baryon, okay, so which is much heavier than this mesons. Okay, so this is what we have seen in our first unit. Okay, so in my next video we will take the revision of our second unit. Thank you for watching.